named as TextNet Topic Plus, Enhancing Text Classification Through Classifier Diversity and Modeling Assembly. The authors are Daniel
Jian.
Thank
Yes.
you, Burcu Bakir Güngör, and Malik Youssef. Do you need help? Just give me a second. Which one is yours? The second one?
Hi everyone, my name is Daniel, a researcher from Al-Quds University, and today I'm so honored to present our research article entitled TextNet Topic Plus, Enhancing Text Classification Through Classifier Diversity and Model Assembly. This work is done in collaboration with Prof. Malik Youssef from Zifat Academic College and Prof. Burcu Bakir from Abdullah Gol University. Much appreciation to both of them. In this presentation, we will go through several key topics as outlined in this outline slide. As a brief introduction, nowadays we are witnessing a vast amount of scientific research papers that is being published on a daily basis. As a consequence, this highlights the need for effective text classification. The main aim of TC is to keep up with all the relevant published work by assigning each document a predefined category according to its content. Manual classification, while feasible, is labor-intensive, time-consuming, and susceptible to errors. In this aspect, machine learning-based text classification has emerged as a powerful alternative, leading to enhanced classification efficiency and reduced manual effort. One significant challenge when training a machine learning algorithm is the sparsity and the high dimensionality of the textual data sets. A single document may comprise hundreds to thousands of unique terms, leading to a vast feature space. As we know, the majority of those features are irrelevant, redundant, or may contribute to noisy data, leading to increased computational training time, may lead to the problem of overfitting, and for sure can degrade the classification performance. Therefore, effective feature selection is crucial to address the following problems. Feature selection is an important pre-processing technique that aims to identify and retain a subset of the most relevant features that aim to represent the whole data set. In text classification context, we aim to represent a document with a reduced number of highly representative and highly discriminative features. When applied on textual datasets, we may obtain several key benefits as shown in this slide. Recently, we have witnessed a recent direction that suggests the use of topic modeling as a feature reduction technique. Topic modeling is unsupervised learning technique that aims to infer latent semantic structures within extensive textual corpus. In other words, it aims to extract the core themes embedded within the corpus. Topic modeling usually produces two main byproducts. The first one is the topic word matrix, where each topic is characterized by a probability distribution over words, and a document topic distribution matrix, where each document can be viewed as a distribution of topic proportions. Apart from its usage or original usage as a topic discovery tool, it has contributed significantly to the text classification as a topic projection technique, where each or the topic proportions from the document topic matrix can be used as features for document representation. However, its usage as a feature selection technique has been sparsely explored in the extant literature. Among minor studies, we have proposed TextNet topics, a novel topic modeling-based feature selection for text classification. Unlike the traditional approach, which aimed to select individual meaningless words, it tends to select cohesive topics as features, offering more structured, more semantically meaningful document representation. As we can see here, it tends to not only perform dimensionality reduction, it tends also to enhance the model interpretability by selecting, as we say, human-centric topics as features. Despite its key strengths, it has a single limitation, or one of the limitations is relying in the M component on the random forest only. While random forest is a robust classifier, however, relying on a single model tends to introduce model bias, limit generalization, and reduce the overall robustness. Different classifiers may capture distinct data patterns, and no single model can perform the best across all data sets. Several research papers has been proposed to enhance TextNet topics, as we can see here. However, none of these has focused on the M component. In this study, we have proposed an ensemble-based TextNet topic classification approach that tend to integrate multiple machine learning algorithms, incorporating two voting schemes, such as soft and hard voting, which aim to harness the classifier diversity to improve the predictive accuracy, enhance the generalization, and for sure reduce the risk of overfitting. Now let's move to our enhanced approach, TextNet Topic Plus. Before we move forward, we need to know that it mainly consists of four main components: the T, G, S, and M components. Now, regarding the T component, it aims to employ the latent Dirac allocation, a widely known topic modeling algorithm, which is applied on a pre-processed data sets to produce the two byproducts. However, in our study, we have used the first byproduct, which is the topic word matrix. In the second component, the G component, it aims to utilize the two inputs. The first one is the set of the K topics extracted from the previous stage, along with the training bag of word data set to construct K topic-based sub-data sets. As we can see here, each sub-data set corresponds to a specific topic. It's a part of the training data, however, it contains only the words that resides in that topic. Similarly, we do that for all topics until we gain K topic-based sub-data sets. These will be directed now to the S component. Regarding the S component, it will analyze the topic-based sub-data sets in order to score and rank the topics based on their classification performance. Here we utilize the stratified Monte Carlo cross-validation approach along with a random forest model in order to create a score. This is like repeated for n times to create the mean performance. Here we can select any performance metric as a topic score. For example, accuracy, F1 score, you can select anything related to your context. After repeating this K times, we will have K ranked topics. Now, these ranked topics will be used in the M component, the final component, to select the top R topics to train the ensemble classifier that we have mentioned earlier. But here, in order to visualize this component, let me introduce you to this animation. In this component, we accumulate the top-ranked topics in a sequential order. Starting from the first topic, each time we add topics sequentially. Afterward, we create a corresponding training and testing sub-data sets. These will be directed to the ensemble classifier. For instance, if we take the first topic set, its corresponding data will be applied to 5 machine learning algorithms, then it will be evaluated through a testing data. Here, each document will take 2 outputs, the predicted class and the predicted probabilities. This will be repeated for like all the documents, and then the result will be directed to either hard voting, where we take the majority votes as the final class, or the soft voting, where we take the highest average probability as the final class. Then we will gain the performance for the first topic set. Similarly, for the second topic set, until we get its performance metric. After repeating this, we will get this performance table, and we will take at the end the best topic set that provide the best performance to train our ensemble classifier. To analyze our approach, we have utilized 2 main data sets, like COVID data set and World of Science data sets. Their class distributions are shown in this table. We have made several text pre-processing steps, started from cleaning, normalization, stop word removal, stemming, and tokenization. Regarding the experimental setup, we have implemented the whole framework through 9 workflows. Regarding the topic modeling, we have utilized the parallelized LBA in 9 with a configuration of 20 topics per 20 words per topic. Regarding the validation strategy, as we have said, we have applied the stratified Monte Carlo cross-validation with 10 iterations. Each time we divide the data into 90% training and 10% testing. Now, finally, let's mention the experimental results. First of all, we have evaluated the baseline TextNet topics among different individual classifiers, starting from the SVM, random forest, logistic regression, XGBoost, and gradient boosting. As we can see from this figure, if we plot the F1 score versus the number of topics, we can see that the SVM performed the best, while gradient boosting here performed the lowest. Afterward, we can see the random forest. In the second data set, we can see the opposite. Here we can see the gradient boosting performed the best, while SVM performed the lowest. However, for both data sets, we can see that XGBoost have a stable performance, which is great. But now, if we apply our ensembling approach, we can see here an enhancement over all accumulated top-ranked topics. Moreover, if we apply our approach to the second data set, we can see the same. These tables summarizes the best performing models, the previous model and the enhanced approach. We can see our approach with the soft voting performed the best. Again, regarding the World of Science data set, we can observe similar trend. As a conclusion, in this study we have proposed an enhanced approach called TextNet Topic Class, which address the limitation of a single model dependency on TextNet topic, the original one, by integrating multiple classifiers and incorporating 2 voting schemes. Finally, ensemble learning with TextNet topics leads to superior classification performance by leveraging classifier diversity. Thank you, but let me end it with a special thanks to my professor, Professor Malik Youssef, for all his support in my scientific journey. Much appreciation to you, Professor Malik. And I would like to thank, for sure, my father for all his support. Without him, I won't be standing in front of you. Thank you so much. Thank you. No question?
No, Everything clear.
Even you understand or you don't understand
Everything
them. Everything is clear.
Somewhere in between. Okay, thank you very much. Dan, since we have a
No, it's a very good work and it's applicable in the business, so good job.
Thank you so much. Thank you. Much appreciation.